Quantum cryptography is a fascinating field that leverages the principles of quantum mechanics to ensure secure communication. Unlike classical cryptography, which relies on mathematical algorithms, quantum cryptography uses the laws of physics to guarantee the confidentiality and integrity of data. One of the key concepts in quantum cryptography is quantum key distribution, QKD, which enables two parties to securely establish a shared encryption key. This key is then used to encrypt and decrypt messages, ensuring that only the intended recipients can access the information. The beauty of quantum key distribution lies in its security guarantees, which are based on the fundamental properties of quantum mechanics. For example, the Heisenberg uncertainty principle states that it is impossible to measure both the position and momentum of a particle with absolute precision. This principle forms the basis of quantum key distribution, as any attempt to eavesdrop on the communication would inevitably disturb the quantum state of the particles, alerting the legitimate users to the presence of an intruder. This inherent security feature makes quantum cryptography highly resilient to attacks, offering a level of protection that is unmatched by classical encryption methods. In fact, researchers estimate that quantum cryptography can provide security levels that are exponentially higher than traditional cryptographic techniques. For instance, a quantum key can be used to encrypt a message in such a way that it would take a classical computer billions of years to crack the code, making it virtually impossible for hackers to decipher the information. The potential applications of quantum cryptography are vast, ranging from secure communication networks to financial transactions and government communications. In recent years, there has been a growing interest in implementing quantum cryptography in various industries to safeguard sensitive data and protect against cyber threats. As the field continues to advance, researchers are exploring new ways to enhance the efficiency and scalability of quantum cryptographic systems. One promising development is the use of quantum repeaters, which can extend the range of quantum communication over long distances. By overcoming the limitations of quantum entanglement, quantum repeaters pave the way for the creation of a global quantum communication network that is secure from end to end. The future of quantum cryptography holds great promise, with the potential to revolutionize the way we secure our digital information and ensure privacy in an increasingly interconnected world. Quantum mechanics is a fascinating branch of physics that deals with the behavior of particles at the smallest scales. One of the most intriguing aspects of quantum mechanics is the concept of superposition, where particles can exist in multiple states simultaneously until they are observed. This phenomenon challenges our classical intuition, but forms the basis of many quantum technologies, including quantum cryptography. Another key principle of quantum mechanics is entanglement, where particles become interconnected in such a way that the state of one particle is instantly correlated with the state of another, regardless of the distance between them. This non-local connection defies classical notions of causality and has been the subject of numerous experiments and studies. Quantum mechanics also introduces the idea of uncertainty, as described by Heisenberg's uncertainty principle, which states that the more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. This inherent uncertainty at the quantum level has profound implications for cryptography and information security. In terms of numbers, quantum mechanics has led to the development of quantum computers, which have the potential to perform calculations at speeds exponentially faster than classical computers. For example, a quantum computer with just 50 qubits could theoretically outperform the most powerful supercomputers in existence today. This exponential increase in processing power could revolutionize fields such as cryptography, drug discovery, and optimization problems. The field of quantum mechanics continues to push the boundaries of our understanding of the universe, offering new insights into the nature of reality and the possibilities of technology. Quantum key distribution, QKD, is a revolutionary method for securely sharing encryption keys between two parties using the principles of quantum mechanics. One of the key features of QKD is its ability to detect any eavesdropping attempts, thanks to the fundamental properties of quantum particles. When a quantum key is transmitted between the sender and receiver, any interception or measurement of the key alters its quantum state, alerting the legitimate users to the presence of an intruder. This unique feature makes QKD highly secure and virtually immune to hacking attempts. In fact, researchers estimate that QKD can provide security levels that are exponentially higher than traditional cryptographic methods. For example, a quantum key can be used to encrypt a message in such a way that it would take a classical computer billions of years to crack the code, ensuring unparalleled security for sensitive data. The security of QKD is further enhanced by the phenomenon of quantum entanglement, where particles become interconnected in a way that their states are instantly correlated, regardless of the distance between them. This non-local connection ensures that any tampering with the quantum key would be immediately detected, making QKD a robust solution for secure communication. In terms of numbers, QKD has seen significant advancements in recent years, with researchers achieving record-breaking key distribution rates and distances. For instance, in 2020, a team of researchers set a new record by distributing quantum keys over a distance of 421 kilometers using a satellite-based QKD system. This achievement marked a major milestone in the field of quantum cryptography, demonstrating the feasibility of long-distance secure communication using quantum principles. As the technology continues to evolve, the scalability and efficiency of QKD systems are improving, paving the way for widespread adoption in various industries. With the potential to revolutionize data security and privacy, quantum key distribution holds great promise for the future of secure communication. Classical cryptography has been the cornerstone of secure communication for centuries, relying on mathematical algorithms to encrypt and decrypt messages. One of the most widely used classical encryption methods is the RSA algorithm, which is based on the difficulty of factoring large prime numbers. In contrast, quantum cryptography leverages the principles of quantum mechanics to ensure secure communication, offering a level of security that is fundamentally different from classical methods. While classical cryptography relies on the computational complexity of mathematical problems, quantum cryptography uses the laws of physics to guarantee the confidentiality of data. Interestingly, quantum key distribution, QKD, can provide security levels that are exponentially higher than classical encryption techniques. For example, a quantum key can be used to encrypt a message in such a way that it would take a classical computer billions of years to crack the code, making it virtually impossible for hackers to decipher the information. In terms of numbers, the security benefits of quantum cryptography are staggering. Researchers estimate that quantum key distribution can offer security levels that are orders of magnitude higher than classical encryption methods, providing a level of protection that is unmatched in the digital age. Furthermore, quantum cryptography is not susceptible to attacks from quantum computers, which have the potential to break many of the commonly used classical encryption algorithms. This unique advantage positions quantum cryptography as a promising solution for securing sensitive data in an era of rapid technological advancement. Quantum cryptography offers a myriad of security benefits that set it apart from traditional cryptographic methods. One of the key advantages of quantum cryptography is its ability to provide unconditional security, meaning that the security of the system is based on the laws of physics rather than computational complexity. This inherent security feature makes quantum cryptography highly resilient to attacks, offering a level of protection that is virtually unbreakable. In fact, researchers estimate that quantum key distribution, QKD, can provide security levels that are exponentially higher than classical encryption techniques. For example, a quantum key can be used to encrypt a message in such a way that it would take a classical computer billions of years to crack the code, making it practically impossible for hackers to decipher the information. The security benefits of quantum cryptography are further enhanced by the phenomenon of quantum entanglement, where particles become interconnected in such a way that their states are instantly correlated, regardless of the distance between them. This non-local connection ensures that any tampering with the quantum key would be immediately detected, making QKD a robust solution for secure communication. In terms of numbers, the security advantages of quantum cryptography are staggering. Researchers have demonstrated record-breaking key distribution rates and distances, showcasing the scalability and efficiency of quantum cryptographic systems. For instance, in 2020, a team of researchers set a new record by distributing quantum keys over a distance of 421 kilometers using a satellite-based QKD system. This achievement marked a major milestone in the field of quantum cryptography, demonstrating the feasibility of long-distance secure communication using quantum principles. The potential applications of quantum cryptography are vast, ranging from secure communication networks to financial transactions and government communications. As the technology continues to advance, the security benefits of quantum cryptography will play a crucial role in safeguarding sensitive data and protecting against cyber threats in an increasingly interconnected world. While quantum cryptography offers unparalleled security benefits, it also faces several challenges and limitations that need to be addressed for widespread adoption. One of the main challenges is the issue of scalability. Current quantum cryptographic systems are limited in terms of the number of users they can support simultaneously. As the number of users increases, the complexity of managing quantum keys and ensuring secure communication also grows, posing a significant scalability challenge. Another limitation of quantum cryptography is the impact of environmental factors on the transmission of quantum keys. External disturbances such as temperature fluctuations, electromagnetic interference, and background noise can introduce errors in the quantum communication channel, affecting the reliability of the system. Researchers are actively working on developing robust error correction techniques to mitigate these environmental effects and improve the overall performance of quantum cryptographic systems. In addition, the cost of implementing quantum cryptography remains a barrier to widespread adoption. Building and maintaining quantum key distribution networks can be expensive, requiring specialized equipment and infrastructure. As the technology matures and becomes more mainstream, the cost of quantum cryptographic systems is expected to decrease, making it more accessible to organizations and individuals. Despite these challenges, the potential of quantum cryptography to revolutionize data security and privacy is undeniable. With ongoing research and advancements in the field, many of these challenges are being addressed, paving the way for a future where quantum cryptography plays a central role in securing our digital communications. Quantum cryptography, with its unparalleled security benefits, has found a variety of real-world applications across different industries. In the realm of finance, quantum cryptography is being explored for securing financial transactions and protecting sensitive data. The potential of quantum key distribution, QKD, to provide unbreakable encryption has attracted the attention of banks and financial institutions looking to enhance the security of their digital assets. In healthcare, quantum cryptography holds promise for safeguarding patient information and medical records. The ability of quantum cryptographic systems to detect any unauthorized access or tampering makes them ideal for ensuring the privacy and integrity of sensitive healthcare data. Quantum cryptography is also making its mark in the field of government communications and national security. Government agencies are increasingly turning to quantum cryptographic solutions to protect classified information and secure communication channels against cyber threats. The adoption of quantum cryptography in these sectors underscores the growing importance of data security and privacy in the digital age. Interesting numbers and statistics further highlight the impact of quantum cryptography in real-world applications. For instance, researchers have achieved record-breaking key distribution rates, with quantum keys being transmitted over long distances using satellite-based QKD systems. In one notable experiment, quantum keys were distributed over a distance of 421 kilometers, showcasing the scalability and efficiency of quantum cryptographic networks. The potential applications of quantum cryptography are vast, with estimates suggesting that the market for quantum cryptographic solutions could reach billions of dollars in the coming years. As the technology continues to evolve and mature, the real-world applications of quantum cryptography are expected to expand. offering new opportunities for securing data and communications in a wide range of industries. Recent research and developments in the field of quantum cryptography have yielded exciting advancements and breakthroughs. One notable area of focus is the development of quantum repeaters, which play a crucial role in extending the range of quantum communication over long distances. Quantum repeaters are devices that can amplify and regenerate quantum signals, allowing for the creation of secure communication channels over hundreds of kilometers. Researchers have made significant progress in improving the efficiency and reliability of quantum repeaters, paving the way for the realization of a global quantum communication network. In a groundbreaking experiment, scientists successfully demonstrated the use of quantum repeaters to distribute quantum keys over a distance of 1,000 kilometers, setting a new record for long-distance secure communication. This achievement represents a major milestone in the field of quantum cryptography, showcasing the potential of quantum repeaters to revolutionize secure communication on a global scale. Another area of active research is the development of quantum-resistant cryptographic algorithms. With the advent of quantum computers, traditional cryptographic methods are at risk of being compromised. To address this challenge, researchers are exploring new encryption techniques that are resistant to attacks from quantum computers. One promising approach is the use of lattice-based cryptography, which offers security guarantees even in the presence of quantum adversaries. Recent studies have shown that lattice-based cryptographic schemes can provide robust protection against quantum attacks, making them a viable solution for securing data in the post-quantum era. The ongoing research in quantum-resistant cryptography is essential for ensuring the long-term security of digital communications and data storage. These developments highlight the dynamic nature of quantum cryptography research and the continuous efforts to enhance the security and reliability of quantum cryptographic systems. The future implications of quantum cryptography are vast and hold great promise for revolutionizing data security and privacy. Researchers predict that the market for quantum cryptographic solutions could reach billions of dollars in the coming years, reflecting the growing demand for secure communication technologies. In terms of numbers, quantum cryptography has seen significant advancements in key distribution rates and distances. For example, researchers have achieved record-breaking key distribution over long distances, with quantum keys transmitted over hundreds of kilometers using advanced quantum repeater technology. This progress marks a significant step towards the realization of a global quantum communication network that is secure from end to end. Looking ahead, the integration of quantum cryptography into existing communication networks could transform the way we secure our digital information and protect against cyber threats. Industries such as finance, healthcare, and government are expected to benefit greatly from the enhanced security provided by quantum cryptographic systems. As quantum technologies continue to evolve, the future implications of quantum cryptography extend beyond secure communication to include quantum-resistant cryptographic algorithms and quantum computing. These developments are poised to shape the future of data security and encryption, ensuring that our digital information remains protected in an increasingly interconnected world. Recent advancements in quantum cryptography have led to record-breaking achievements, such as distributing quantum keys over distances of hundreds of kilometers. The market for quantum cryptographic solutions is projected to grow significantly in the coming years, reflecting the increasing demand for secure communication technologies. Quantum repeater technology has shown promise in extending the range of quantum communication, paving the way for a global quantum communication network. These developments underscore the transformative potential of quantum cryptography in reshaping data security and privacy.